Okay, should we get started?
Yeah, no, that sounds great. This is the first webinar we're doing in the next sort of phase of the ISoRED Webinar Seminar series. We're going to be kicking off today with a special session all around the 40th anniversary of the Chernobyl disaster. So our question is, what have we learned and what questions still remain? And we have two speakers today, which will be tackling the sort of research from both the epidemiology and dosimetry perspectives, followed by a panel discussion about what questions are still left to be answered for this important research topic. I'd like to introduce today's chair, which is Dr. Lisa Cahoon. She's a senior investigator in the Radiation Epidemiology branch at the National Cancer Institute, and her research focuses on cancer and pre-cancer risk associated with environmental radiation exposure. She's conducted extensive research on this topic related to radiation-related risks among children that were exposed to fallout, and also the cleanup workers following the Chernobyl disaster, with a particular emphasis on thyroid nodules and breast cancer in these populations. So I'll leave it to Lisa to sort of run today's seminar with all her experience, and I look forward to it.
Thank you, Angela, for organizing this webinar and for the kind introduction. So this series of talks marks a significant milestone, the 40th anniversary of the Chernobyl nuclear accident. Over 4 decades, Chernobyl has remained a pivotal event in the history of environmental and public health, offering lessons in radiation exposure, emergency response, and the long-term health consequences for affected populations. Bringing together leading experts in dosimetry, epidemiology, and radiation biology, these presentations provide a comprehensive exploration of the achievements and persistent challenges in understanding and mitigating the impacts of this disaster. So we're honored to welcome a diverse group of experts who bring a wealth of experience and insight to today's webinar. Our speakers and panelists represent a variety of fields and backgrounds, and I hope they'll ensure a rich and engaging discussion for all attendees. So please join us in welcoming them as they share their knowledge and perspectives throughout this session. So the first speaker today is Dr. Vladimir Drozdovich. He is a senior associate scientist at the National Cancer Institute in the United States. His research program focuses on dose reconstruction for individuals and population groups exposed to ionizing radiation from environmental sources, including nuclear accident releases and fallout from atmospheric nuclear weapons tests. His talk today is on the achievements and challenges in post-Chernobyl dosimetry. So welcome, Vladimir.
Yeah, thank you, Lisa, for your presentation. I will try to share my screen. So can you see my presentation?
Yes, we can see it.
Okay.
Thank you.
Yeah, okay, great. So I will talk about achievement and challenges in post-Chernobyl dosimetry. This is disclaimer from NIH. You can read it. And just to remind you, Chernobyl nuclear reactor accident occurred on April 26, 1986 at Unit 4 in Ukraine. It's more than 40 years ago, and this accident resulted in widespread contamination of territories of Belarus, Ukraine, and the western part of Russia, as well as entire Europe and also touch entire North Hemisphere. It's multiple radiation epidemiological studies were conducted to evaluate the possible health effects of consequences of the accident. And these studies consider 2 major target population groups. It's a general population or residents of territories contaminated after the accident. And another group, it's the Chernobyl cleanup workers. It's individuals who took part between 1986 and 1990 in the decontamination and recovery activities within the 30-kilometer zone around the Chernobyl power plant, including Chernobyl site. Okay, let's talk about dosimetry. So The reconstruction of individual radiation doses for the study participants is an important part of radiation epidemiological studies. So we developed the complex dosimetry systems for post-Chernobyl studies conducted by NCI and Belarus in Ukraine. In general, these systems allow to compute multiple possible dose sets or realizations for the entire study population, accounting for sources of shared and unshared errors. And just to explain, the geometric standard deviation of 1000 dose realization, which we use for study participants, characterize the uncertainty in individual doses for given subjects. For general population, increase in thyroid cancer and other thyroid disease following the exposure to iodine-131 and other short-lived radioiodine isotopes is the major health consequences of the Chernobyl accident. And radioiodine isotopes, particularly iodine-131, are among the most radiologically significant fission products, and they have strong tendency to accumulate in the thyroid gland, where iodine delivers significant radiation doses. And in first approximation, the thyroid dose from iodine-131 is proportional to the consumption of milk and other dairy products, and inversely proportional to the thyroid mass. And this scheme shows how it's occurred. So it's released from accident, it's a deposition with wet or dry conditions, contaminated grass, which was eaten by cow, produced milk, and then people drink this milk. So inside Chernobyl studies in general populations included several cohorts. It's a Belarusian American cohort of almost 12,000 individuals who were younger than 18 years old at the time of the accident. And the same population subgroup created Ukrainian American cohort of more than 13,000 individuals. And for both of these cohorts, one of the criteria to inclusion was availability of direct thyroid measurements, which allow to estimate iodine-131 activity in the thyroid. Another two cohort, it's a Belarusian and Ukrainian cohort of peasants exposed in utero and early life. It's in total more than almost 6,000 individuals. And also Chernobyl tissue bank in Ukraine, which consists more than 4,000 individuals who developed thyroid cancer after the Chernobyl accident. And the following exposure pathways were considered for dose reconstruction in these study populations. It's intake of iodine, first of all, which is the most important for thyroid exposure, intake of short-lived radiotellurium and radioiodine isotopes, external radiation from radionuclides deposited on the ground, and also ingestion of cesium isotopes with the foodstuff. This table summarizes radiation doses to the thyroid gland in general population. Sorry, in the considered cohort. And you can see that doses are pretty high in Ukrainian, Belarusian American, Ukrainian American cohort. It's more than half gray exposure to thyroid. And also significant doses were delivered to individuals exposed in utero, as well as to Chernobyl bank, and also GSD, which is a characterization of uncertainty. It's lower in Belarusian American and Ukrainian American cohort because they have direct thyroid measurements, and I will talk about this later. For Ukrainian cohort of peasants exposed to utero and Chernobyl tissue bank, there is almost no measurements done in study subjects. The uncertainty is much higher with GSD around 3. For Chernobyl studies about Ukrainian cleanup workers, we conducted case control study of leukemia and related disorders, case control study of thyroid cancer, parental radiation and general mutation in the offspring, so-called RIO study, and germline genetic variants associated with host susceptibility to the severe COVID-19 disease. And again, there is two modes of exposure for cleanup workers. It's during cleanup mission at Chernobyl site in the 30-kilometer zone, and also some of these cleanup workers were residents of neighboring settlements. For cleanup workers, the major exposure pathway was, of course, external radiation, as well as we consider inhalation of iodine and short-lived radioiodine tellurium isotope for the thyroid cancer study. And during residence, as usual, residents of the contaminated areas Cleanup workers also receive exposure from external radiation, intake of iodine for thyroid gland, and ingestion of cesium isotopes. Dosimetry system for Chernobyl cleanup workers, we developed time and motion method named RADROOM. It was used to estimate external doses during the cleanup missions for all studies. And the RADROOM technique, it's pretty straightforward and calculate external dose as a product of exposure rate and irradiation time with accounting for shielding properties of the local environmentals. And dose reconstruction model developed for the general population were used to estimate doses during the period of residence. These tables summarize radiation doses to cleanup workers, and depending on the study, target organ for exposure was different. For case control study of leukemia, it was bone marrow. For thyroid cancer, of course, it's thyroid. And for trio study, it was gonads. And you can see the mean doses in this study populations were not trivial. For the external exposure, it's around or more 100 milligray, which is from low to medium dose range. And also uncertainties in the dose estimates. Individual GSDs are, let's say, moderate from 1.8 to 2. One of the big advantages of Chernobyl studies in Chernobyl dosimetries, we conducted pretty extensive assessment of uncertainties, and I will talk about this a little bit. Uncertainties and errors in dosimetry of post-Chernobyl radiation epidemiological studies associated with instrumental radiation measurements of human and environmental samples, inherent uncertainties arising from the stochastic variability of the parameters used in exposure assessment, lack of knowledge about true parameter values, and other sources. And another important source is the human factor uncertainties, which associated with poor memory recall, resulting in incomplete, inaccurate, or missing responses during personal interview with study subjects. And this interview were conducted long time after exposure. I will not talk about instrumental radiation measurements and measurements error. It's pretty straightforward. Regarding inherent uncertainties, for example, for thyroid cohort studies, this is a scheme of dose calculation. You can see deposition density, result of measurement personal interview, and biokinetic ecological models allowed us to calculate ecological activity, and also in the thyroid in time integrated ecological activity, which is together with the dose factor and the thyroid mass values allowed to calculate ecological thyroid dose or model, so-called model thyroid dose, and then based on measurements, it would scaling to receive instrumental thyroid dose. And all of these parameters are sources of shared and unshared errors. For example, for shared errors with iodine deposition density, the settlements, which was shared among all subjects resided in these settlements, parameter of radioecological model, and unshared errors, it's individual measured iodine thyroid activity, thyroid mass for given person, and answers to questions administered during the personal dosimetry interview. This scheme shows two-dimensional Monte Carlo simulations of cohort dose realization. At the beginning of each iteration, we define the sample for distribution values of shared parameters, which were applied for entire cohort or the part of the cohort, depending of parameter, and then for each individual with sample values of unshared parameters and calculated his doses. It was done during the one dose realization for entire cohort, and then repeated 1,000 times. So we have solid matrix of 100 doses for each cohort members, and 1,000 dose realization for one individual represents individual stochastic doses for the entire for this cohort member. What is interesting, it's a contribution of shared and unshared errors, because shared errors, they bias the risk estimation. It's important to take them into account, but when we calculated ecological doses, the width of this distribution. This is 1000 dose realization for entire cohort. One line, it's a dose realization for the cohort. And width of this distribution shows that contribution of shared errors, it's pretty high for ecological or model dose calculations. But in this particular cohort, because all of study subjects have direct thyroid measurements, when we calibrate ecological doses by measured iodine-31 activity, it's virtually eliminated all sources of shared uncertainties. And you see the width of this distribution is pretty low. But again, this is applied for only this cohort, Belarusian American and Ukrainian American, where all cohort members have direct thyroid measurements. In utero cohorts, its situation is slightly different. Another source of uncertainties, it's the human factor uncertainties. All these studies are retrospective. Again, we conduct them starting in late 90s. It was already almost 15 years after the accident. And to calculate doses, we need individual information to estimate realistic, reliable doses. For general population, in brief, we collect data of residential history, dietary habits, behavior, and so on. For cleanup workers, we need detailed work history, its location, dates, duration of activities, and dietary habits for internal radiation during residence. And such information was collected through personal dosimetry interviews with all study subjects, and for cohorts, also mothers, if person was younger than 10 years old at the time of the accident, and from all cleanup workers or their proxies. Proxies were colleagues for disease cleanup workers. For example, in leukemia study, we have a lot of disease cases. For ideally, residential history and dietary data for population or work history for cleanup workers should completely and precisely reflect what's happened in the distant past at the time of the accident. But in reality, the poor memory recall resulted in incomplete, inaccurate, and missed answers during the personal interview that was conducted long time after exposure. So we conducted so-called human factor uncertainty studies in general population, in screening cohorts. We evaluated this uncertainty for the Belarusian American cohort and Belarusian cohort of persons exposed in utero. This cohort members or their mothers were interviewed at least 2 times in 1996, 2001, and 2001, 2007. And for in utero cohort, they were interviewed, mothers were interviewed in 2012, 2017, and 2018, 2022. We evaluated the consistency of responses from 2 personal interviews and their influence on model-based and measurement-based doses that were calculated using 2 questionnaires. For cleanup workers, we also evaluated this human factor uncertainty using the following approach. We have historical description of cleanup activities reported by cleanup workers shortly after the completion of their mission, with recollection time about 2 weeks and a little bit more, and doses calculated based on these historical work activities. We called reference dose, and also we trace and locate in interviews the same cleanup workers and also their proxies during a personal interview conducted in 2011-2015 with mean recollection time about 27 years, and also compare doses. I don't go to details. We compare doses calculated during these 2 questionnaires and analyze what is the reason for difference and how this difference in answers will influence the doses. So summary for these human factor uncertainties, this show a range of relative errors, and you can see, and also these numbers don't reflect, let's say, variability around center estimates. This is represents the shift in doses. For example, for general population, if we don't have measurements, model-based doses can be shifted by 10 times, 20 times from the central estimates. For measurement-based doses, because there are measurements, this factor is much less. It's about factor of 2. As the same for cleanup workers, it's factor about 4 or 5, up to 6, for doses to be shifted from the center estimates. So we identify the human factor uncertainties as important source of error in doses. So further activities and questions remain. Even it's almost more than 40 years after the accident, so dosimetry for these Chernobyl studies are not finished. This is an ongoing process. And for example, the NCI now conducted study of cohort study of germline genetic variants associated with several COVID-19 disease in cleanup workers. And this study creates the need to develop a methodology to estimate lung doses from inhalation from different radionuclides for study participants, and this is ongoing activity. We are working on this now. Another example of ongoing activities is assessment of uncertainty in prenatal doses for the Belarusian cohort exposed in utero, including a detailed analysis of uncertainties associated with the iodine biokinetic model for pregnant women. Another example is improvement of doses for Chernobyl tissue bank and calculation of doses to female breast for residents of contaminated areas. What can be done, in my opinion? For example, for the dosimetry of screening cohort, we are now also working on the following. So having a multiple questionnaire for the same person provide opportunity to compose, let's say, artificial best possible questionnaire by replacing misses or imprecise answers in one questionnaire with accurate answers from other questionnaires. So we are working on this using machine learning algorithm, but this approach required careful consideration and detailed analysis of impact on model-based and especially measurement-based doses, and recollection time, and also measured iodine activity for measurement-based doses. For cleanup workers, RADRU methods provide the dose estimates used in epidemiological studies with reasonable degree of reliability, but these methods required a lot of labor efforts and also rather expensive. And also we need a sufficient detailed work histories for cleanup workers to calculate doses. Therefore, there is a need to develop alternative, simplified method, which will be based on key parameters defining exposure. However, we may face the problem of addressing the variability of doses across the study population and within a particular group of cleanup workers, because this variability is pretty huge. So, and for both screening cohort and cleanup workers dosimetry, human factor uncertainty should be carefully considered in exposure assessment with specific attention for the studies involving individuals without instrumental radiation measurements, because it's pretty huge in this case. And we need to develop methodology to account for human factor uncertainties in those estimates, and also it's important to assess how these uncertainties affect the epidemiological analysis. It's a list of our current collaborators from National Research Center for Radiation Medicine in Kiev in Ukraine, Barnasian Medical Biophysical Center of Moscow in Russia, from Institute of Nuclear Problems in Minsk in Belarus, and the Republican Research Center for Radiation Medicine and Human Ecology in Gomel in Belarus. And this is not all collaborators, a lot of people were retired, and I also acknowledge their contribution to the development of the dosimetry system for Belarus and Ukraine. I conclude my presentation, but I would like to invite you to Radiation Epidemiology Dosimetry courses, which will be held in NCI and Rockville in the United States in December 14 to 17. Registration now it's open, and you can visit this course website. Registration is free, and but this course will be only in person, but with recording of lectures that will be available after the course will be finished. Thank you.
Thank you, Vladimir. That was an excellent presentation. So I think we can do questions at the end in regard to the panelists, if that's okay, so that I have time to introduce the next speaker, Dr. Zhenya Aspanmova is a scientist in the Environmental and Lifestyle Epidemiology branch of the International Agency for Research on Cancer in Lyon, France. Her talk today will summarize key findings from epidemiological studies on cancer and non-cancer health effects in cleanup workers and other populations affected by the Chernobyl nuclear accident. She will highlight important research questions that remain unresolved and require further investigation. So I welcome Zhenya.
Thank you, Lisa, for the nice introduction. Can you hear me and see my slides?
Yes, we can.
Good. Thank you. Hello, everyone. I'm very pleased to have an opportunity today to overview the key epidemiological findings collected over the 4 decades of working on the Chernobyl research. And however, there is still a number of open scientific questions that are important and that needs further attention and to be addressed. I will not repeat what Vladimir just said so perfectly in his presentation, but what I want to say that the Chernobyl accident appeared to be and remains to be the most severe and the most painful page history in the nuclear industry. And we still can learn directly a lot from this very painful experience. I would like to summarize the key findings following the this outline of exposed population, and of course I will speak about the findings and the health effects among the cleanup workers, among the individuals who were exposed in childhood and adolescence. Another important category of affected people, those who were exposed in utero. Definitely in the focus of our presentation today is the general population who continues to reside in the radioactively contaminated areas. And the last but not least, these are unexposed offspring born to exposed parents. Let me start with the key findings received about the thyroid cancer radiation risk in cleanup workers. The first study that had been published by Dr. Kesminiene and co-authors in 2012 was focused on the thyroid cancer risk in Belarusian, Russian, and Baltic states cleanup workers. The feature of this case control study was inclusion of study participants, not only men, but also women. And you can see that the median thyroid dose in this case control analysis was about 70 milligray, and evidence of linear dose response, significant dose response been seen in this analysis. More recently, a case control study on Ukrainian male cleanup workers has been published by the Gudzenka et al., where the median age at exposure and age at diagnosis are similar to what been reported by IARC study. The mean thyroid dose is rather high compared to the median thyroid dose in the IARC study, but also there is an indication of increased thyroid cancer risk in the cleanup workers, although the findings in the study was borderline significant. Another important health outcome that brings a lot of attention, this is the risk of hematological malignancies, in particular leukemia in the cleanup workers. Let me start with the findings from, again, IARC coordinated case control study in Belarusian, Russian, and Baltic states liquidators. And you can see that although the median bone marrow dose in cases was rather low, there is an indication of positive association of all leukemia, chronic lymphocytic leukemia, and non-CLL leukemia risk in relation to bone marrow dose. The point estimates are positive, although there is no, they didn't reach the level of statistical significance. Another evidence on elevated leukemia risks came from a cohort of Russian liquidators who were followed up for leukemia incidents from 1986 through 2007. And they presented only the risk estimates for non-CLL leukemia, where the overall risk for the total follow-up period was elevated but not statistically significant. And interestingly, the highest significant risk was observed in the period closest to the accident date. So in 1986-1997, the excess relative risk of 5 per grade being observed in this cleanup workers cohort. Another important findings came from the case control study in Ukrainian cleanup workers and published by Zablotska et al. In 2013. This study also showed the significant dose association between all types of cell types of leukemia, but also the risk, radiation-related risk for non-CLL and CLL leukemia were comparable and statistically significant. This study brought the also active discussion concerning the possible mechanisms of radiation-induced CLL, and these findings also requires further investigation and replication from other study subsets. This is the summary of what we know about non-thyroid cancers in cleanup workers. Most of the reports are based on the comparison of observed versus expected site-specific cancers. And I highlighted few of those reports that, to my opinion, seems important. First of all, I wanted to show that there was a report on possibly increased breast cancer risk in Ukrainian female cleanup workers. And also there was a report showing the elevated esophageal cancer proportional incidence ratio in the liquidators from the Baltic countries. Studies on all solid cancers combined both incidence mortality data in the Russian male liquidator cohort also showed a significantly increased radiation-related risk both for mortality and incidence due to all solid cancers. Besides the cancers, there are other important non-cancer outcomes, and this slide also presents the key findings that also change, some of them change our perception of the mechanisms and doses that are responsible for occurrence of certain effects. First of all, that is the study by Vorgul et al., who published on positive dose response for cataracts in a Ukrainian cohort of cleanup workers at doses that much lower than initially believed to be a cataract radiation cataract threshold, and that really the study became the one that that stimulated the revisions and further discussions on possible lower threshold for radiation cataractogenesis. Recent reports showed the exposure-related increase of frequency of chronic cerebrovascular and neurocognitive disorders in Ukrainian male cleanup workers. But these studies require further research and more data to confirm these possible associations. Increased risk of cardiovascular diseases being reported in the Russian male liquidators cohort, or among those liquidators who were on mission during the first year after the accident, so from April 1986 through April 1987. Let me move to the thyroid cancer and non-cancer thyroid disease risks in relation to iodine-131 exposure in those who were children and adolescents at the time of the accident, and also who were in utero. First reports showing increased number of thyroid cancers among children had been taken with great skepticism. First of all, because there was little knowledge about the carcinogenic effect of iodine-131, and also little knowledge about the radiation-related risk in young populations, exposed populations. Next two slides summarizes the key findings received from the cohorts that Vladimir already introduced to you. This is the UCRAM and BELAM cohort. These are two cohorts with the unified screening protocol aimed at detection of thyroid cancers and non-thyroid non-cancer diseases in those who were less than 18 years old at the time of the accident. Another important feature of these two cohorts is the individually reconstructed doses that are based on the direct thyroid measurements in each study individual. You can see that there is a good agreement about the risks of thyroid cancer between the countries using the prevalence or incidence data. The confidence intervals are large, but they are overlapping, and that it makes the risk estimates statistically compatible. This slide also shows the results coming not only from the cohort, but also from case control studies on thyroid cancer risk among the children and exposed as children and adolescents. And you can see that each study reported the positive risk, and there is a clear indication of significant association of iodine-131 exposure and lifetime risk of thyroid cancer in this population. It's not only important to understand the magnitude and the dose relationship for the thyroid cancer. It's also important to identify the factors that could modify radiation-related risk of thyroid cancer. And one of those factors is iodine prophylaxis. In the paper published by Zhupunsky et al. In 2019, it was clearly shown that the iodine prophylaxis decreases the radiation-related risk of thyroid cancer among those individuals who had took the stable iodine tablets. And this finding also needs the further reproduction or to be reproduced in other studies. But at the same time, this is an important finding that will have and could have a serious implication in case of preparedness for future nuclear emergencies and protection of protection of the affected populations. Beside the thyroid cancer, important attention was given to the thyroid nodules risk, also in these two cohorts, UCRAM and BELAM. And you can see that in both countries, there is a clear indication of positive significant association between the risk of all thyroid nodules and especially neoplastic thyroid nodules in relation to iodine-131 thyroid dose. These findings are important because that makes justifies the medical follow-up and medical surveillance of individuals with detected thyroid nodules for timely interventions and diagnostic measures if necessary in case of pathological transformation, malignant transformation of these neoplastic nodules later in life. In this slide, you can see the key findings coming from UCRAM and BELAM in utero exposed cohorts. And also, despite that it's a very small number of thyroid cancers in UCRAM cohort, we still see the positive risk, elevated risk of thyroid cancer following in utero exposure to iodine-131, although not statistically significant. But in both countries, you also see that there is an indication that thyroid nodules are associated, risk of thyroid nodules associated with the exposure to iodine-131 received during the period of intrauterine development. Again, not only thyroid cancer and thyroid nodule play a role in the evaluation of the thyroid health in this affected study group, there are also a number of important thyroid non-cancer diseases, and it has been shown that there is a positive association between increased prevalence of thyroid peroxidase antibodies in those individuals in the UCRAM and BELAM cohorts. And this finding also could have a clinical importance in terms of the monitoring the changes that could appear with time in the individuals with the elevated ITPO levels. Another finding was both observed in BELAM and UCRAM cohorts. This is a positive association between iodine-131 thyroid dose and subclinical hyperthyroidism that also requires further monitoring of the thyroid health in these two screening cohorts. Little evidence was received for dose association for hyperthyroidism. And with the next part, I would like to highlight the findings on cancer risk among the residents of radioactively contaminated territories. First of all, I would like to speak about the ecological studies that IARC is doing to monitor the cancer incidence in the most contaminated areas in Belarus and Ukraine in collaboration with the Ukrainian and Belarusian researchers using the data from the National Cancer Cancer Registries. Also, we thank to Vladimir for his collaboration, helping us to estimate Rhine average cumulative breast doses and other organ doses that allows us to perform the informative analysis of the cancer incidence data. As for the breast cancer incidence, we found little evidence of association between Rhine average cumulative breast dose and breast cancer incidence in Ukraine and Belarus. So again, don't forget, this is an ecological study, so it just to see if there is some huge, if there is to detect, to spot some big changes in the cancer incidence risk. At the same time, we understand that the need for analytical studies with individually reconstructed doses could be more precise in terms of risk characterization in this population. Another study that been published recently was focused on hematological malignancy incidence in Belarus over the period 1986-2019. We found no evidence of radiation-related increase of lymphoma, multiple myeloma, and total leukemia in relation to Rhine average cumulative bone marrow dose. However, there was a suggestion of an elevated risk of the myeloid leukemia, and this finding requires further monitoring of the incidence trends in this population. Very important findings came from the NCI studies on breast cancer risk in pregnant and lactating women at the time of the accident. And you can see that in these two cohorts in Ukraine and Belarus, the findings are in line with each other. And interestingly, there was no indication on increased risk, breast cancer risk in those women who were pregnant at the time of the accident and within the 2 months after, but there was clear indication of elevated breast cancer risk in those women who were breastfeeding and lactating at the time of the accident and within 2 months after in Belarus. And again, I would like, it's almost end of my presentation, I would like to summarize what we know about the health risks in exposed offspring born to exposed parents exposed as a result of the Chernobyl accident at this stage. The most informative and the most recent and state-of-the-art study came from collaboration between NCI and Ukraine. It's a trio study, and the germline de novo mutation were explored in 130 children who were born from mother-child pairs composed from cleanup workers and evacuees. And you can see that the further cumulative gonadal dose at conception were much higher compared to the maternal cumulative gonadal dose. The overall conclusion of the study was that individuals do not appear to experience elevated de novo mutations from their parental exposure. And this is a good result, although we still see that there is a need to continue to explore this important issue. So, and this is the last slide of my presentation. Of course, we learned a lot over these 40 years, but we all know that many radiation-related diseases could have a long latency period, and that justifies the continue of follow-up and monitoring of the important populations that are being highlighted in this presentation. We have open scientific questions, and it's not the the complete list of those questions, but I try to highlight the ones that also presents, to my opinion, presents an importance. So of course we learned about the thyroid cancer a lot, but there are other non-thyroid solid cancers that also the radiation-related risks should be well characterized. There is a need to learn more about the role of potential effect modifiers, for example, for thyroid cancer, such as role of iodine supplementation, role of stable iodine prophylaxis, effect on variation of radiation-related risk with time since exposure or age at exposure. For the chronic lymphocytic leukemia, as I already said, there is a need for more evidence of dose response and also additional insights on possible mechanisms of radiation-induced CLL. For non-cancer diseases, there is definitely a big need for additional insights and additional research on radiation effects for functional and structural thyroid diseases and cardiac and cerebrovascular diseases as well. And at the end, again, as the last but not least, this is a need for continuation of research on transgenerational effects in unexposed offspring who were born to exposed parents. And with that, I thank you for your attention.
Thank you, Zhenya, for that wonderful presentation. Okay, so with this, I think I will introduce our panelists, and we can open up the discussion. So our first panelist today is Dr. Vadim Shumak. He is an expert in radiation dosimetry and medical physics. He's head of the Laboratory of Radiation Dosimetry at the National Research Center for Radiation Medicine, Hematology, and Oncology, which is part of the National Academy of Medical Sciences of Ukraine. So welcome, Dr. Shumak.
Hello, thank you for a very nice introduction. So just one correction, I'm head of laboratory in NSRM, retired last December. So I'm working in a different place. And I still remember all sorts of my experience in Chernobyl dosimetry. So I would like to attract your attention to one of, actually several of slides, when compared uncertainties associated with model-based and measurement-based dosimetry. And if you remember, the difference is striking, and there is about tenfold different. And this is just an example of one or two studies, actually. And as a it really so for me it was surprising that epidemiologists are still happy with such uncertainty. My understanding is that the most important is to have doses unbiased. So on average, they are not overestimated or underestimated. Of course, as a physicist and dosimetrist, I would prefer to have more precise. And now we are coming to the point of what lessons can be learned from Chernobyl and similar accidents or incidents, and what can be done better than it was in Chernobyl. And to my opinion, the conclusion is that, of course, the doses to organs which are of interest, like thyroid gland for thyroid cancer, germ-like cells for hereditary effects, or red bone marrow for leukemia, or lens for cataract, those doses are different from the dose use the event with personal dosimeters or with their substitutes. But still, if you have some solid basis, then you can apply some corrections. You apply some models to convert from the measured doses to the doses of interest. But if you don't have such, you're in trouble. So actually, that's what we had in Chernobyl. Because speaking about liquidators, a majority of them either had no doses at all, or had doses of very dubious quality, or doses biased by different reasons. And again, the sources of this situation are very, very, very different. But then in Fukushima, it was repeated to some extent, because the very early liquidators, they had problems with dosimetry, and the early times is the times where the doses are highest. So I would suggest to think about either some better planning for dosimetry at times for respondents and for populations, but also one need to realize that such dosimetric monitoring programs cannot cover all population, because in no preparedness plans it is included that population will have personal dosimeters, for instance. And now we are coming to the point of search for practical retrospective dosimetry methods. You know that there are a lot of biodosimetry. There is physical dosimetry with glass or semiconductor elements in personal gadgets, but all of them have deficiencies. And now it falls to my attention that there is very good candidate for such emergency dosimetry is simple table salt. Very available, but also it's quite good OSL, optical stimulated luminescence dosimeter. which can be engaged immediately after the event by public, just going to kitchen and collecting some salt and carrying as a regular dosimeter. But so that's a discussion point, because if you speak about some emergency like large scale release or a nuclear attack or large scale terrorist attack, it is possible to engage population into such protective measure, and eventually no individual doses, quite cheap and quite reasonable. But I also understand that the generals usually are prepared for the past wars. So now we're considering scenarios which are coming from Chernobyl experience, but who knows what will be. However, such the salt dosimetry, it also could be used for verification of a medical exposure dose. You know that another big domain in epidemiology is epidemiology of patients irradiated, particularly they have those estimates which are calculated by software at time of exposure of radiotherapy or interventional procedures, but usually they are not validated by independent physical measurements. And again, table salt is very cheap complement to the calculated doses. But nevertheless, now we have discussion. So I'm just throwing some ball into this discussion. I don't have answers, and I expect that participants will share their views on this topic. Thank you.
Thank you, Dr. Shumak. So I'd like to introduce another panelist, Dr. Vladimir Senko. He is an accomplished radiation biologist and molecular epidemiologist and professor at the Department of Radiation Molecular Epidemiology at the Atomic Bomb Disease Institute in Nagasaki University, Japan. So welcome to the panel. And then the final panelist is Dr. Lindsay Morton, who is a senior investigator and director of the Radiation Epidemiology branch in the Division of Cancer Epidemiology and Genetics at the U.S. National Cancer Institute. So welcome to all the panelists. It's wonderful to have you here. And I think we can start potentially with some of the questions in the chat for our first two speakers, if that's okay. So one of the questions was about relating to Dr. Shumak's comments, was related on, you know, what information needs to be collected and would improve the data on the general public in terms of dosimetry. Would it be enough to collect names and contact information and then do follow-up interviews? So that goes out to Vladimir and perhaps Dr. Shumak as well.
Well, it's a good question. So, first of all, we need to distinguish radiation protection issues and collection of information and measurements for future epidemiological studies. First of all, population should be protected in case of any accident. It should be sheltering, evacuation, iodine prophylaxis, and so on. In terms of collection of information from Chernobyl experience and from Fukushima experience, it's measurements, conduct measurements of in environmental, in air contamination, deposition density, measurements in foodstuff like cow's milk or any food which is important for given area. And also the most important, it's measurements in human. It's measurements of iodine in steroid, measurements whole body count of different radionuclides. And we even conduct special study to model exposure to iodine-131 based on just modeling, based on deposition density, based on modeling using iodine measurements in milk and other foodstuff, and then based on iodine measurements in human. So even if you use measurements in foods, iodine in food, it will not improve a lot of results of dose reconstruction compared with just modeling without any data. But if you have direct steroid measurements, it provides you very reliable doses. Another important part, especially in the early time of the accident, when deposition of radionuclides, contamination of foodstuff and humans are the maximal, it's behavior of individuals. If you would like to calculate the individual dose, not population general, but individual dose, and even for population average group dose, it's important to learn what was behavior of these people. For example, in several papers, we suggested that in case of nuclear accident, people will complete some kind of diary, what they did every day, what they eat every day, but it may be not realistic, but this is ideal case, you know, to have this information for each study participants, for each individual. So this is my answers.
Thank you. Thank you very much.
Okay, I can add just 2 words to support what Vladimir told. I share completely his statement, but to give you some feeling of inter-individual variability in practical cases in Chernobyl. So to justify estimation of individual doses versus group or average, population average. So in Pripyat area, so the range of spread of individual doses was up to 3 orders of magnitude. And while in one of our liquidator studies, in leukemia study, the dynamic range of doses was 7 orders of magnitude, from very high to completely minuscule. And simply using metrics like distance from reactor or time after the accident can give very little information about individual doses. One needs to reconstruct individual behaviors, individual routes, to learn more about what this person was doing, and then you come to more narrow and more.
Okay, thank you. When the next question in the chat, I think, goes to Zhenya. Could you please comment using general population as a reference when calculating cancer risks in cleanup workers? Can the cancer risk be underestimated, as it can be assumed that cleanup workers might be a selected group from the population with better health before cleanup work? What are your thoughts on this?
Thank you for this very good question. Of course, you know, the completeness of the cancer cases ascertainment in the general population and also in the cleanup workers, it's a valid question. Again, from the studies that I presented today, this information comes from the large group of cleanup workers. That's part of them are under regular medical surveillance, but not all of them. So in that case, I would assume that the diagnostics of cancer cases among them, it's not differ much from the diagnostics among the general population. And it makes the comparison valid using the general population cancer incidence rates. Of course, the main question is that through this comparison, we cannot address the important confounders that also play a role in certain site-specific cancers, for example, like alcohol consumption or BMI or physical activity. This really, there are some reports that shows that maybe cleanup workers population could be different in some extent compared to general population. In that case, I see that could present some how to say challenges of what is the most appropriate population to use, unexposed population to use to compare the cancer incidence between the cleanup workers and other population groups. I hope I could answer the question.
Thank you, Zhenya. Do you think that the validity of the SIRs is roughly similar across cancer types? I'm thinking specifically about types that are more likely to be screen detected versus other types. What are your thoughts on that?
It's my personal experience. If you think about the thyroid cancer analysis in Ukrainian cleanup workers, the first before the analytical study with individual reconstructed dose being developed, we did the SIR. Of course, there was a lot of question how, if it's the increased SIRs in the cleanup workers could be the results of more regular screening or more scrutinized medical surveillance of this group. But as we saw from the analytical study later on, that SIR results, they are valid. They could serve as an indicator for and be like a signal for a need to do the analytical study with individually reconstructed doses.
Thank you. The next question is about the slide, quote, measured thyroid activity has virtually eliminated all sources of shared uncertainty. Does that suggest that the models tend to underestimate doses? Vladimir, I think that was for you.
No, it's not suggested that model tend to underestimate doses or overestimate doses. We are talking about contribution of shared errors to the reconstructed doses. And the reason why these direct thyroid measurements eliminate, because when we scout model-based dose by direct thyroid activity, measured activity, this equation also involved activity of iodine in the thyroid calculated using the model for the time of measurement. So this is a ratio measured to calculated activity. And calculated activity also involved all these radioecological parameters models which were used to calculate doses and therefore divided one by another, resulted in this elimination of shared errors, whereas the radioecological model is the main source of these errors. It's nothing about overestimation or underestimation.
Thank you. Thought we could potentially provide Dr. Senko the opportunity to for a brief introduction of his work and maybe some questions on this different aspect. Welcome to the panel, Dr. Senko.
Yes, thank you very much. Thank you very much for inviting me to this exciting meeting and opportunity to share a bit some highlights of our research. It's a bit far from dosimetry, but we heavily rely on dosimetric data in our research. So today I would like to share these highlights, which are clinical pathological characteristics. Oh, sorry, can I? No. So first would be clinical pathological characteristics and evolution of the Chernobyl thyroid cancer. Can you see my slides well?
Yes.
Thank you. Then radiation-related thyroid cancer prognosis, and then a few words about the crosstalk between environmental exposures and genetic factors predisposing to thyroid cancer. First of all, let's talk a bit about clinical pathological characteristics. And the question in the focus here is whether radiation-related thyroid cancer is pathologically more aggressive than sporadic. This slide shows data obtained in cooperation with our colleagues from Ukraine. And please take a look at the lower parts of these graphs that show the invasive features of thyroid cancers. And as you can see, radiation-related thyroid cancer display more frequent, higher frequencies of invasive features as compared to sporadic cancers. These differences are particularly well seen in children in childhood, patients, still seen in adolescent patients, and just a bit seen in adults. So the answer to the question about the comparative aggressiveness of radiation-related and sporadic thyroid cancer would be likely yes, radiation-related thyroid cancer looks more aggressive at presentation as compared to sporadic thyroid cancer. Next, what I would like to mention is that Chernobyl cancer changes in time. There are some descending trends and some ascending trends. The descending trends include less frequent fusion gene drivers for the tumors, decreasing tumor size, some particularities in tumor growth patterns. And what is more important, that the overall invasiveness of the Chernobyl thyroid cancer declines with time. The ascending trends include the higher frequency of point mutation drivers like BRAF point mutation and some other points, and the number of small-sized tumors is growing. And there's also an age trend in tumor aggressiveness. At presentation, tumors, thyroid cancers in children look more aggressive than in adolescents and in adults. The second point is to try to get insights into the question whether radiation-related thyroid cancer has worse prognosis than that in sporadic thyroid cancer. This is the result of our collaborative study with the colleagues from Russia, where we took Chernobyl thyroid cancers, radiation-induced, which is we called, and sporadic thyroid cancer. When we compared the chance for recurrence, we observed no difference between the radiation-related thyroid cancer and sporadic thyroid cancer. So the chance of recurrence of radiation-related thyroid cancer is comparable to that for sporadic thyroid cancer. We did not observe etiologically specific risk factor for recurrence, and therefore it was suggested that radiation-related thyroid cancer would better be diagnosed, treated, and followed up in the same way as sporadic thyroid cancers. And finally, so the answer to this question, to the question of prognosis, is likely no. There is no difference in prognosis of two etiological forms of thyroid cancer. And finally, a few words about the environment exposures and predisposing germline genetic variants that predispose to thyroid cancer. Well, we know that that there are individual effects of environmental factors such as radioactivity, internal irradiation from iodine-131. We know that there is effects of stable iodine. But what we do not know well enough is whether there is what is their joint effect and whether they can modulate each other effect. Well, for environmental exposures, we do know that there are effects, but there are no clues for this interaction. And in our recent study with colleagues from Belarus, we found, we again confirmed that stable iodine diminishes or decreases harm from radioactive iodine. So there's decline in for their interaction. That we also found that some predisposing variant can positively interact to each other, which means that they increase their effect sizes with an increasing number of risk alleles. But what was the most important, and which is good news, that predisposing genetic variants and radiation exposure reduce each other's effect. They do not enhance it. And that would be all from me for a moment. I would be glad to take part in discussion. Thank you.
Thank you. Thank you, Dr. Senko. So one of my questions for you is about what your perspective is on a latency period for radiation-induced thyroid cancer. And related to that, your thoughts on the progression of thyroid nodules over time in a radiation setting, and if you have any ideas about or recommendations for monitoring, the large amount of thyroid nodules that are found through screening in some radiation settings like the Fukushima accident and also Chernobyl.
Well, these are questions that would be a bit difficult to answer. But with regard to latency, what we do know that latency is negatively associated with thyroid dose, which means that the lower the dose is, the longer the latency would be expected. And also what we do know that thyroid doses in younger in individuals exposed at younger age are higher. So there are in this setting there are too many multicollinear factors that need to be considered very carefully, and maybe we should, to carefully investigate this issue, we need to use or step away from the proportional hazard models and think of other means of careful evaluating what we can expect, what kind of factors can contribute more or stronger to affect the duration of the latency period. And what we do not know also with regard to the Chernobyl thyroid cancer is whether the recurrences may be shifted toward later terms. So far, we do not see higher chance of recurrence in patients exposed to radiation, but we still do not know what is going to be happening in the years to come. So we should keep an eye on those patients. And with regard to Fukushima issue, well, the doses to the thyroid in Fukushima residents were much less than in Chernobyl, and maybe we can get a bit back to dosimetry and cancer risk researchers, and to clarify whether to ask once again whether the radiation risks at very low doses are really, do they really exist? I'm not talking about the threshold dose, but at very low doses, how the risks are pronounced. That would be my answer.
Thank you. Thank you very much. So I'd like to ask the last question for Dr. Morton. I'm wondering if you have any remarks on the molecular epidemiology advances that have occurred as a result of this accident, what you see as the future, and what are some exciting new areas that we can take the molecular work with the advances in technology.
Yeah, thanks very much. It's been really wonderful to hear the previous speakers, and I think they've really set up my answer to this question very well. There have been amazing advances in genomic technologies, particularly the ability to short read and now long read whole genome sequencing, looking at both somatic changes, so changes in the DNA of tumor cells themselves, as well as germline DNA, so that's the inherited genome. And I think these advances in technologies have been able to complement in the last decade or so the amazing kind of existing interdisciplinary scientific platform that these Chernobyl studies have really represented. So for decades, there have been amazing collaborations amongst physicists and epidemiologists and clinicians and pathologists and radiobiologists. And now when we can add in some more molecular techniques, because of the foresight of collaborators to collect both tumor tissue and germline DNA, we've been able to really get at some of the questions. So Zhenya talked about the transgenerational effects. Can we understand whether the cleanup workers and other residentially exposed individuals may have passed on any mutations to their offspring? And so far, the answer with the sequencing technologies available to date is that we're not seeing any such transgenerational effect. And then from a tumor DNA perspective, one of the things I'm really excited about is the fact that we've been able to, for the first time, really translate what radiobiologists have shown for decades, which is that DNA double-strand breaks are the most consequential form of DNA damage from ionizing radiation, and that those DNA double-strand breaks actually translate into carcinogenesis. So we can see those fusion-driven tumors being caused by radiation, and then even beyond that, one of the questions we've been asking and that I think we want to continue to press on in the coming years is whether we can identify which tumors were radiation related or radiation induced as opposed to sporadic. And I think we're just starting to get at that. Our first analyses don't identify what we would consider as a unique biomarker or a unique signature of radiation-induced tumors. And I would think every radiobiologist would have predicted that, because we know that ionizing radiation damage occurs randomly across the genome. So unlike chemical carcinogens, which may bind to certain regions of the genome or only cause certain changes, ionizing radiation damage is not specific in that same way. So the randomness in some ways is in and of itself a signature, but that's really hard to quantify. That being said, we're getting closer, I think, in some of the recent analyses, because we've been able to use fresh frozen tumor samples from the Chernobyl tissue bank collected by our colleagues at the Institute of Entomology and Metabolism. We're getting a little bit closer and really trying to understand the idea that it's not just all fusion drivers, but only specific fusion-driven tumors appear to be consistent with having been caused by the accident. And according to the initial data that we're looking at, none of the mutation-driven tumors are in fact radiation-related. And so it calls into question or it raises a terminology question. For example, when an individual has a history of radiation exposure, understandably in the literature to date, we've been using the terminology that it's a radiation-related tumor. But in fact, our data would suggest that many of those may have occurred by chance alone, and were not actually radiation related, and that only a subset of the fusion-driven tumors are caused by radiation. If we can continue to pursue this line of research, then I think it will really help us to continue to understand the true impact of the Chernobyl accident. And, as Dr. Senko was saying, the much lower doses from Fukushima, but indeed whether there are radiation-induced tumors that have been identified in that population also.
Thank you very much. Thank you to everyone for your wonderful presentations and for participating. So with that, I would like to say goodbye to everyone and once again advertise the REB Radiation and Dosimetry course that's occurring in December. So please check it out. So thank you. Thank you.